All right, so let's take a look at what we had found. Originally, we have T2 equals T1 minus, we had 1 over CP, but we had V2 squared over 2CP. So we can write this. And so if we rearrange this as a delta T, so we could write this as T2 minus T1 and I think what we can do is pull out a T1. That's our reservoir temperature. So if we do that, we have T1 times T2 over T1 minus 1 equals negative V2 squared over 2CP. And this is what we had found for a polytropic process was T2 over T1. That was equal to P2 over P1 to the gamma minus 1 over gamma. So we can replace that in this equation. So we'll have P2 over P1 to the gamma minus 1 over gamma minus 1. And we can solve that then for V2. So let's plug this in first. T1 times P2 over P1 to the minus 1 over gamma. Then that is minus 1. Equals to negative V2 squared over 2CP. And we can solve this for V2. So T1 over 2CP that is T1 times 2CP, right? And that should be the average. 2T1 times CP is and we can write it like this. I do believe that'll work out if we flip the sign here. We can get rid of the negative on the V2, and then this should be to the 1/2 power. So now if we know what the tank temperature is, and that might just be stored at room temperature, like the environment temperature, and we have an idea of the pressure difference between the environment and the tank, we now have an expression for the average velocity in that at the outlet of the nozzle. So we can get an idea of the speed of the air or whatever gas we have in that container as a function of pressure.